now on, we are going to use this type of diagrams to describe quantum algorithms. The lines here denote qubits. The most significant is the highest, so this state here is 0, 1. And on these lines we are going to place these squares which will denote quantum gates in order of the application from left to right. So here we apply Hadamard gate to both qubits. And you can see that we have two qubits here, so the whole transform, this transform must be a matrix 4 by 4. What is the look of this matrix, since the dimensionality of the space is 4? It is easy to compute this matrix. You just need to multiply hash by hash to compute a tensor product or a Kronecker product, which is this tensor product, and it is this matrix. Okay, it is generally true that if you have two different operators which are applied to two different qubits, then you can represent it like this Kronecker product of these operators which is applied to the Kronecker product of the composite system of the qubits of the initial system. And this identity can be easily proved, and I will leave you this as an exercise. And just one small hint how to prove this identity. You can both sides of this identity are vectors, so you can choose some index at random, and to prove that for any random index, the component with this index in this vector equals to the component with the same index in this vector. Okay, what if we have this situation? The dimensionality of the space is still 4, so the whole matrix here must be 4 by 4. But we don't have anything here to compute this tensor product. Actually, we have, if nothing happens here, then we can place an identity operator here, which does nothing. And the matrix of this transform will be this. And the very same situation here, the matrix will look like this, which is square root of 2. Identity, 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 and minus identity. The CNOT operator we are going to represent like this. So this bit is controlled, and this, where we have this thick dot, is the control bit. And if we have this transform, for example, 3 qubits here, so the dimensionality is 8, and this matrix must be 8 by 8. And again, we can easily compute it. So it is this matrix. These are just parts 4 by 4 in this matrix. Okay, now a little bit more complicated question. What is the look of this matrix? Again, it is a matrix 8 by 8, and there are only 3 possible ways of obtaining this matrix 8 by 8 by a tensor product. So we have to multiply 3 matrices 2 by 2, or 1 matrix 2 by 2 by 4 by 4, or maybe this way. So we already have a matrix 4 by 4, which is C0, and matrix 2 by 2 maybe is this identity matrix 2 by 2, but we don't have to put it from the left or from the right of this C0. We have to put it inside, somewhere in the middle, and there's no way we can do this. But maybe we can decompose this C0 matrix on a tensor product of 2 smaller matrices A and B. Each is 2 by 2 matrix. So if we could do that, then we could represent this operator here like this. But again, there's no way we can do this, because matrix C0 cannot be decomposed in the tensor product of 2 smaller matrices. It appears that this matrix, this gate C0, acts on both states, and we cannot implement it as an acting on separate states separately. So there are no operators which can be applied separately to our states to obtain the action of this C0 operator. And we already met this situation with entangled states, where there was no separate state for different particles. And this situation is quite the same. So those states were entangled, and this kind of operators, like C0, they are entangling operators. And they are the main obstacle in creating the physical implementation of quantum computer. This is the most complicated operators to implement. Okay, this is all good, but we don't still have the look of this matrix. Can we even do that? Can we obtain this look? Yes, we can. Let's have a look how any matrix A here, so this is some unknown matrix A, how this matrix acts on a basis vector where we have only one which is on the position K. So when it's just a simple matrix multiplication, so we multiply each row by this column, and the only index which survives in this row is index K. So the result of this matrix multiplication is the kth column of the matrix A. And this is our hint how we can obtain the look of any unknown matrix if we know how it acts on basis vectors. For example, if we take our favorite vector 1, 0, 1, for which K is 6, so it has 1 on the place 6, and we know that the action of this operator is this, so the control bit here is 1, and it has to flip the last bit, which is controlled. So this state is transformed, is mapped by this operator to this state, which is the vector where we have 1 on the place 5. So, okay, it would be 5 here for this vector. And so we can obtain the whole look of the matrix, which is this. And you can see that the 6th column here, it has 1 on the place 5. This is the column we have just computed. Okay, there remains only one thing that we need to go further. We are going to need this expression for the n-qubit Hadamard transform. Many algorithms which we will learn will start like this. There are many qubits, and to reach these qubits at the start of the algorithm, we apply Hadamard transform. And since we are going to need the look of this matrix, instead of computing this enormous tensor product each time, we are going only once prove this expression. But let's take a look at this first. So we can see that this transform here maps any input vector to a sum of all vectors, of all basis vectors in our space, the dimensionality of which is 2 in the power n. So we have 2 in the power n of basis vectors, and they all present here in this sum. Please note that this y here is a vector, and this y here is a number, some binary representation. So here we count all the numbers from 0 to 2 in the power n minus 1, and here we add up the vectors which are encoded by these numbers. And the coefficients of these vectors are either plus or minus 1, and they depend on the input vector. The thick dot product here is actually the inner product in this space. So it's just for each component we have this multiplication, and then we add up all the results of this multiplication of these bits modulo 2. Okay, how to prove this expression? I would like to prove it by induction, and actually I will leave it to you as an exercise, but I will help you with the base. So for n equals to 1, we will have h1 of x, which is 1 divided by square root of 2, and the sum of y from 0 to 1 minus 1 x thick dot y, which is 1 divided by square root of 2. If y equals to 0, when we have just this 0 vector, because this thick dot product gives us 0, and then we are going to have this minus 1 in the power x and 1 here. So if x equals to 0, we will have vector plus, and if x equals to 1, we will have vector minus. So the base is okay, we have proved it, and the induction step I am leaving you as an exercise, but if you don't really like this exercise, you can see this proof on the slides to this lecture. Okay, now we have everything we need to continue and to learn some basic quantum algorithms and even to build our own quantum computer, which will implement one of these algorithms. And this quantum computer is going to be, the qubits there will be encoded by the polarization of photons. Not only polarization of photons, by photons. But this is our plan for the next week, and this lecture is over. And I hope to see you next time, and I wish you good luck with the week test. Goodbye.